Welcome, virtual class. Today we're going to take a look at angles of polygons. So here we have some various polygons. All of them are convex polygons, and we'll really want to focus on convex polygons for what we're doing here. And we're going to take those polygons, and if we pick one vertex of the polygon, so starting over here on the quadrilateral, pick the vertex and draw all the diagonals that you can from that vertex to a non-adjacent vertex. While in the quadrilateral, that's just the one diagonal. Notice when we draw that in, we end up with two triangles. And if we take the angles of the triangles, we know the sum of those angles is 180 for each triangle. And that gives us that the sum of the angles of the quadrilateral then is 360 degrees. If we follow that same process and take a pentagon, pick one vertex again, doesn't matter which one, and draw in all the possible diagonals to the non-adjacent vertices, we end up with three triangles at 180 degrees each. And so 3 times 180 gives us a total of 540 degrees for that polygon. For the hexagon, again, pick one vertex, draw the diagonals. This time we end up with 4 triangles. So we see that 4 times 180, we have 720 degrees for the sum of the angles there. That gives us then the idea for the formula for the sum of the interior angles of a convex polygon. Notice that when we had 4 sides, there were 2 triangles formed. 5 sides formed 3 triangles, and 6 sides formed 4 triangles. So the number of triangles formed is always 2 less than the number of sides. So the formula then is given here. The sum of the angles, S, is 180 times the quantity n minus 2. We can take that then and apply it in example 1 here, where we have this mall food court in the shape of a regular pentagon. Remember that a regular pentagon means all the angles and all the sides are congruent. And so if we want to know the sum of the angles, we take the formula S equals 180 times n minus 2. And we have 5 sides, so it's 180 times 5 minus 2, or 180 times 3. And we'd already worked that one out on the last page, so that is 540 degrees for the sum of the angles. Go ahead and try that with the next example here. Pause the video for a moment and try your turn dealing with the octagon window. Now we're going to adapt that formula just a little bit for the measure of one interior angle of a regular polygon. So if we have a regular polygon, we know all the angles are the same, so we can take the sum of the angles, which we know is 180 times n minus 2, and divide that by the number of angles, which is n. So we get the measure of one angle of a regular polygon is 180 n minus 2 divided by n. So here we know that one angle has a measure of 135 degrees. And that has to equal the 180 times n minus 2 divided by n. And just doing our algebra, multiplying both sides by n, 135n equals distributing the 180 180 minus 360. That then leaves us with, if we subtract the 180n from each side, negative 45n equals negative 360, and dividing by the negative 45. N equals 8. So we now know that this polygon would have 8 sides. Pause the video and try the next problem. And for this one, that you should have found that the number of sides is 10. Just like we did with triangles earlier when we learned the angle sum theorem, we're going to apply a similar idea here as we put a little bit of algebra into our geometry. So we know with a quadrilateral, the sum of the interior angles, we worked that out earlier. Sum is 180 times n minus 2. And when n is 4, then that comes out to the sum of the angles being 360 degrees. So here we see we can just add these angles together and set it equal to 360 to find x. Note that r and t both have a measure of 5x, so we can do 2 times 5x, plus s and u also have the same measure, so 2 times 11x plus 4 has to equal 360. So 10x plus 22x plus 8 is 360, or 32x, taking a couple steps here, equals 352, and x equals 11. Now, once again, as we should always do, make sure that you've answered the original question that was asked. So we want to know the measure of each angle. So the measure of angle R is equal to the measure of angle T, which are both 55, and the measure of angle S is equal to the measure of angle U, and those are both 125, plugging back into the original expressions. Give that a try in the next problem. And sorry, but the TV audience does not get to do the exterior angle march. I know that is disappointing. Recall that when we talked about triangles and exterior angles, we found an exterior angle of a triangle by extending one of the sides of the triangle. And that angle adjacent to an interior angle is what we call the exterior angle. We're going to have that same concept here with polygons, and we want to look then at how those exterior angles are related. So if we have a convex polygon, the sum of the exterior angles of the polygon, one of each vertex, is always 360. So we don't even need to really mess with the formula on that one. We just memorize that that is always going to be 360. So in example 4 here, where we have one exterior angle at each vertex of this polygon, and we know that the sum of those has to be 360. So this is a nonagon. That means there are 9 sides, so 9 times the measure of each angle has to equal the total of all of them, 360. And dividing by the 9, we get that A, the measure of each angle, has to be 40 degrees. Try that for the regular regular hexagon shown here, and find the measure of each angle. So for this we have 6 times the measure of an angle, M, has to equal 360, and dividing by the 6 then gives us that the measure of each angle is 60 degrees. So If we know that each exterior angle is 60 degrees, what about the measure of an interior angle? We know the interior angles and the exterior angles have to be supplementary. So that gives us a shortcut. If we have a regular polygon, we can find the measure of each interior angle by just looking at the exterior angles. So this would have to be 120 degrees. That concludes lesson 8.1. And so I will go back to the homework here in case you didn't catch that. And so there is the homework for lesson 8.1.